let's do problem 7 on the constant acceleration worksheet number 4. Here's the problem. It says a physics student skis down a slope starting from rest and accelerating at a constant 2.0 meters per second squared. If it takes her 15 seconds to reach the bottom of the slope, how fast is she going at the end? How long is the slope? Draw velocity versus time graph. So given. So here's my slope. Here's my skier. It's got the poles going there. And then here's a scarf. Okay. Please do not draw a skier without a scarf. Okay. Now, she's starting from rest so that we know V naught equals 0. And we know that the acceleration down the incline is a constant 2 meters per second squared. And we want to know what is her final velocity down here. Okay, so we want V final. And we want to know what delta x is. Her displacement going down the incline. And then we want to draw velocity versus time graph. And we know that this takes place after 15 seconds. I think that's everything we know. So I like to draw a sketch of the problem and put what's given around that sketch. And then what are we trying to find? Well, for part A, it says how fast is she going? I want the final velocity. And then for part B, I want delta x. And then part C, I want velocity versus time. So let's solve. Well, I know the time, I know the initial velocity, I know the acceleration, I want the final velocity. So I look on my kinematic equation list and I say, okay, what equation matches those 4 variables? And it's the first one. And so, so V equals V naught, and let me mark this with part A. V naught is 0 plus 2 meters per second every second times 15 seconds. So V equals, well, 2 times 15 is 30 meters per second. That's the right answer. Now look at the technique I'm using here. I start off with the basic equation that matches what's given and what I'm trying to find. Then I plug in my values with units, and then I box my answer. That's good technique right there. That's what I'd like to see you do. Now for part B, I want delta x, but I don't want to use this final velocity, so I need to find an equation that matches all of this, and I would use the third kinematic equation because it doesn't have the final velocity in it. So if I made a mistake in part A, it won't carry over to part B. So my displacement is equal to my initial velocity times time plus 1/2 my acceleration times my time squared. This is 0, so this whole term goes away. So delta x is now equal to 1/2. My acceleration is 2 meters per second every second times time squared, 15 seconds squared. What is that? Okay, so that cancels with that, gives me 1. The second squared cancels both of those. I'm left with meters. So 15 squared, I believe, is 225? Yeah. And I think I have just enough room here to squeeze in part C. Velocity as a function of time. Pretty easy graph. So I'll just go 5, 10, 15. And then I'm going to go from 10, 20, 30. And this is velocity in meters per second. Just about everybody's labeling their graph when I was grading this problem. You guys did good. So we're going to start here. We end up over here, and it's a straight line. Now, some of you are still plotting points for each second. That takes a lot of time, and you don't need to do that if you know it's linear. Okay? And that is the problem. Any questions on problem 7? Okay, that is all